so LIME just rephrases the interpretation on how we're looking at the coefficients in a regression model. So usually these beta values are used to fit like a line, right? But they also represent how much impact each feature actually has on the system, right? And so if B1 is very large, that means whatever feature we're representing with X1 also must be very important to our model. And we're going to hold on to that idea as we go through this. So I just want to show some formulas on the board that's going to make it easier to explain weighted regression quickly. But essentially with LIME, we're representing all of our features as binary vectors, ones and zeros, which makes it really hard to give any context or weight to these features individually. And so we make up for that by applying weights. And a weight matrix is just a diagonal map with the weights on the diagonals. If anybody's confused at any point, please stop me. This will get kind of math-heavy. I apologize in advance. Yeah, and so I need to do a little bit more setup, which is introduce the concept of RoPE as well. RoPE is a somewhat more modern embedding method, and it's used within the layers of many modern LLMs. And essentially what it allows us to do is encode attention scores, not only by where tokens sit in sequence, but also their relative position to one another. And so what this means is that even when tokens shift, their weights are still relatively similar because we are encoding the data between tokens, not absolutely. So that kind of gets us into why we're even using RoPE for this pipeline. And the main thing comes down to masking. With RoPE, even when we mask, our index shifts don't destroy the structure of the data. So think about like a cosine similarity. And this also means that, like I said, our distance metrics will also remain stable. Now, at a high level, this is what our pipeline looks like. It's quite simple when you're looking at this, but each step is a little bit more complicated, and so I'll go through each part and break it down step by step. But at a high level, what we're doing is just computing those y values for our regression, finding our feature vectors, and computing our weights. So the first step is to get your output from some kind of large model, the model you're trying to explain. So like I said, usually this is in like the billions of parameters, think like a GPT and Anthropic model. And just hold on to that idea because I'll come back to it in a second. But it's important that we separate the generation from the attribution. So the next step is to generate what we call perturbations from this input prompt. And the input prompt is everything you're sending to the model before it generates. So that's our x value. And we represent this input prompt as a set of features. And a single feature is just a span of tokens, which we then aggregate into a single token via a mean. So this means that we can represent anything from a sentence, a paragraph, a message entirely. We can even do disjoint sets. So we can pass like the first and the third message as one feature as well. And this gives us a lot of flexibility in how we actually determine what matters to our model. Now, the other problem with current regression methods is that, or LIME methods, I should say, is that there's no standardized sampling. And as your n, or your number of features, gets large, it gets very hard to properly attribute enough samples such that you can get meaningful regression. There are techniques like leave one out, which often underrepresent the amount of data you need. And it's very easy to oversample as well. And so we propose Sparse-K sampling, which is this formula on the board here, where C and K are both functions of the number of features. Within our paper, we do some experimentation with what C and K should be. For simplicity, I'm not going to get into that now, but the results are in our paper. And like I said, Sparse-K, it reduces the sampling cost while still maintaining accurate attributions, which helps us get like a nice middle ground between under and oversampling. So that gets to the next part of this, which is the input distances. These are how we compute our regression weights. And to do this, we use what is called word movers distance. Now, word movers distance, or in our case, relaxed word movers distance, is Wasserstein distance, but for embeddings. And some of you might not be familiar with Wasserstein distance, but essentially what that is it just lets us grab probability distributions. Okay. And so what this is going to allow us to do is it's going to allow us to take the semantic distance between our base prompt, which is unchanged, and our masked input prompts, which have some features removed from them. And with Wallerstein distance or word move resistance in general, it assumes that each feature is a single embedding, whether that be a word embedding, a token embedding, so on and so forth, which is also why we represent each feature as a single token. So this is just kind of the math behind how we're doing stuff under the hood for our regression. You can take a picture if you want. It's also in our paper, but this is just to help you understand at a little bit of a deeper level.
Quick question, how does Wasserstein distance contrast to like Euclidean distance or even KL divergence?
Yeah, so Wasserstein distance specifically, or word movers distance, I'll say just for this case, because that's essentially what we're using, is it measures not the distance between words. Okay, hold this. It measures like the semantics, whereas opposed to cosine similarity, it will. Okay, hold on, give me a sec. Yeah.
Yeah. So cosine similarity you use when you have two embeddings and then you take it out product, which gives you cosine. So Wasserstein distance comes when you have sets. You have two sets, and in your set A you have vectors, and in your set B you have vectors. So now you want to measure what's the distance. In our case, it's semantic because we have vectors, and then between two vectors, it's cosine. So now it doesn't need to be like that. When people talk about word movers distance, it can just be normal words, and then if you have some way to define a distance between words. For example, if your set A has n points and set B has n minus 1 points, everything's the same. So the distance is less. So it's kind of like when we take input features and mask something, you're removing things. And when you have feature to feature, and you use the feature to feature based similarity or base distance metric. So it's kind of like a compound metric, which will help us here.
So it's not sensitive to the order of the elements in the sets?
Yes, usually it is not sensitive to the order. However, here we take row embeddings for the tokens. So each and every token is encoded with a position. So that makes it sensitive. For example, let's say you have a word repetition. If your sentence is just A, so you have 4 A's, and then A is a token. And there's a feature where you have removed the first token, and another feature is the same thing, you have removed the third token. The difference is, the distances are different because RoPE encodes position.
Yeah, when you were showing that formula for the regression, and you were talking about adding the weights. So, yeah.
Is this
the
linear one?
Yeah, the one
The one before this, yeah.
Yes, one.
Yeah.
So here the order of the inputs it's always the same. So when in the next slide when you do like the matrix multiplications, so what does each regressor represent, or how do you keep the order that always the x1s go to and the x1s have to go?
Right, so suppose we have n features, right? We're going to encode a vector of length n, that's 1s or zeros, and it will always be the case that feature 1 is correlated with index 1, if that makes sense. And so when we take different permutations of 1s and zeros, and when we subtract it, if it matters a lot to the overall attribution score, the bias or the parameter weight will go up significantly more when it's missing. And so when you take like n of those, or in our case, Sparse-K of those, it will show you which spans or matter more to the attribution of the final output, if that answers your question.
Okay, so the order is based on the importance is calculated somewhere else.
I'm not quite sure I understand.
I think that you said that x1 will be always the one with the highest something or...
No. X1 will always be feature 1.
Okay.
Yeah. Does that make sense?
Yeah.
Just another sort of clarification question. So you're taking spans, right?
Yes.
So each
And, well, yes, that is obviously an issue. I believe that because we're using RoPE, the relative positions help a lot with the mean stuff, and then also the, how do I explain this? Sorry, I've never been put on the spot about my paper.
We also tried for a span. We also tried aggregation and then just cosine similarity. So we tried multiple methods, and yeah, RWMD seemed to be the better one, but we haven't dug deep into this step actually. Yeah.
Was there a question?
Yeah. When you're doing your perturbation sampling, you say oversampling, so you can just leave one out, and that would be oversampling.
That would be undersampling. So leave one out essentially just for each feature. We remove only that feature. So if we have 23 features, we only get 23 feature vectors.
So what is the oversampling case?
So oversampling, for example, would be like taking a power set, which would give us like all possible permutations, which would theoretically be the best bound for regression. But when you have like 52 samples, it's 52 factorial. I don't think there exists enough compute to compute that.
Okay. Does it get noisy at that point, or like is it just
So
time?
it's a time thing, really. And we did a hyperparameter sweep using Sparse-K to try and remove some of that noise. And we reported our best metrics at the bottom.
You guys can keep moving.
Yeah, so this is where the original output part comes in. So the cool part about our method is that we've actually removed the reasoning from the attribution steps altogether. So if you didn't know, you can actually run a forward pass over, you can actually run a forward pass over already generated tokens, and you can get what the model thinks is the most, like how likely that specific token is at that position, as opposed to getting the most likely token. And so what this allows us to do is instead of regenerating at every step, we can generate over the reasoning that's already been done by our large model. And with these perturbed inputs and these massive values, we get different probability distributions on these already generated spans. And so it looks something like this. We take we use our small model f of s conditioned on our already generated span. We're going to call it y, that's our ground truth. And we just, we run a forward pass with each one of our perturbed prompts. And then we take the natural log likelihood to normalize them to probability distributions. And then we can take the distance between these using KL divergence, which is how we measure the distribution between probability scores. And so this just goes over what I said. Yeah. And then so we're going to use those as our y values to then fit our regression model. So putting it all together, we have the weights from the Wasserstein distance, or sorry, the word movers distance. We have the perturbed inputs x, which are binary feature vectors. And then finally, we have these y outputs, which are a result of our KL divergence. And so when we fit a regression model using the formula from above, I can go back if anybody needs clarification. No, we're good. We then get our bias terms, and the highest ones represent the most attribution. And so we rank those from greatest to least, and we can determine which spans attributed the most to our output. Yeah, sorry, and then here's some results. Sorry.
Yeah, no, you can go for it. I was just going to ask a question, but you can go for the results first.
Okay, yeah, thanks. So,
if I could add real quick, so what you're regressing on is the KL divergences?
correct.
Yeah.
Yeah, that's what we're fitting for, yeah. So, figure 1 is our method benchmarked against another prime method that we used a lot of inspiration for. That's called gSMILE. It's a very similar process, except that one operates on much lower length spans, as well as closed source models. They're the blue line and we are the red line. So to measure our accuracy here, we repeated their regimen, which was to take some queries from the MMLU dataset and label the words by relative importance. So we hand labeled this, it was about 60 advantage of our method. So the larger solid bars are our Sparse-K method, and the slash bars, I'm not sure if you can see them from where you're sitting, but this is also in our paper. These like bars with slashes going through them, that's traditional like leave one out sampling methods. And as I mentioned before, we were not able to experiment with oversampled results as that would simply just take too much time.
Excuse me, what, can you clarify, what are you trying to get to compare yourself with another method?
Right, so those are the reported scores on their regime, which was essentially to run a attribution-based method on hand-labeled queries from the MMLU dataset, which are essentially multiple choice question answers. And so the question has important subjects in words, right? So it's like Paris is the capital of what country? So in that case, like Paris, country, capital would be very important words, and so they should have a higher feature attribution score.
Like a context heat map.
Yeah,
Yeah.
exactly.
So our output is actually a heat map over features.
Yeah.
Yeah.
And then the data set on the bottom is the same idea, except we operated over paragraphs in sentences from the HotpotQA data set.
And by the way, how do you know, since you are comparing yourself with somebody else, how do you know that your heat map is better than another heat map? Who makes a decision?
Right, so it's not heat maps per se in this case. So essentially IOU intersection over union. So if there's like, we did it at 10, but let's say there's 20 words in a data set, or in a question, right? So 10 words are going to be more important than 10 other words, right? And so we want to see how many of these words we can actually get in our top 10. And so what we're measuring is how many more words, or important words, we're attributing as opposed to the other method, if that makes sense.
But how do you know what are the top 10 words? So
Okay, yeah. So that's a little, I'm not sure what the word for that. It's a little subjective in terms of like which words are more important. I'll give you that. So that's how the other method also benchmarked. So below our benchmark uses HotpotQA, which already has labeled sentences within there saying like these are important for the result. And we did much better on that data set as well.
Sorry. Yep.
Did you find anything on what some of the most important words were? Like, did you find anything on like, oh, LLMs generally look at verbs or nouns or anything like that? Or maybe like a term like solid gold magic card in order to figure out like, oh, this one word is like the most important word?
So not quite, but what we did find is that the context surrounding like words when you perturb them matters a lot more. So if you have like a very rich context, say like a system prompt or something that's like really big, say like a GPT system prompt, when you remove things, you can get away with a lot less samples.
I think he was first and you're next.
And so, if I understand, like your technique is contingent on you just perturbing one of these features at a time. Like you're not perturbing multiple.
No, so we do both.
Okay,
Yeah.
because one thing I was thinking of, like, because you're perturbing the inputs. For example, as an example, could you look at like quantization as an issue where if you were to quantize an input and dequantize it, that's a perturbation that gets caused. And then can you then look at the difference in the output, because sometimes that could be impacted, right, or something.
Yeah, that's not something we looked into, but it seems pretty interesting. Maybe I will look into it in the future.
Oh, good ideas.
Yeah.
That's what I come here.
Perfect.
So, another question would be, did you see any relationship on how close was it to the prompt of the prompt? Like the first or second word, were they more impacted?
Yeah, so in this method, no, but during our experimentation, we also tried gradient-based methods, and what we found was due to attention sync, we believed. Are you familiar with the term? Okay, so essentially the idea is that LLMs attribute a lot more weight in their gradients to the first couple words in a sequence. And what we found when running these gradient-based analysis, introduced by Ritesh at the beginning, is that, yes, a lot of these tokens were front-heavy.
Like how much from it?
Like significantly, like 90% plus.
Yeah.
where actually LLM has everything in context, but still is not able to produce an answer. Or even with everything in context, it's not able to make a tool call. So this is a wrong generation. What we do is we want to see what part of our things that we can control. It's either the system prompt or the way we are presenting the user context. It could be how you're formatting tool output results and whatever it is. So we select features one at a time. So let's say if we want to iterate on system prompts, then we only jump system prompt into sentences that become our features and see what is this wrong generation actually most conditioned on, or which part of system prompt is causing us is more influential. And also, if you know, if it is a tool call, you would know what a right tool call would look like. So you can also do the same thing with a positive sample. And then with these heat maps, currently we haven't really closed the loop. It's just humans who are sitting there and optimizing the prompts. That's something good. Yeah, exactly.
I was also wondering with something like Distilver or distilling models, in that situation, you're using KL divergence to narrow it down. I guess I was just thinking, something with that, maybe you could, with this, then take that and then assign weights to certain things that you want the training to highlight versus other things. I don't know, just sort of like an
Yeah,
idea.
that's actually the original old distillation. Actually, currently we call distillation as just generate data sets from parent model and then train your child model on it. But the original distillation paper actually ensures not only the data set, it ensures actually your log props also converge to the parent model. So you are actually distilling the exact distribution. It's actually a known thing. However, in LLMs, I'm not sure if someone had done that.
Did you have any more? Oh, we have time for about 2 more questions if you guys.
Yeah, so I remember hearing about Lime in the context of vision models a couple of years ago. And from what I understood, Lime was shown to not be very good at attributing, what the researchers did was they had a backdoor on the image, right? And they were trying to see, the backdoor would cause the model to produce some obvious nonsense, a wrong answer. And they were trying to see, can Lime detect the presence of the backdoor? Can it attribute the correct patch? And Lime totally failed compared to a blank image where everything is the correct answer. So I'm wondering, you were comparing to other attribution methods, but is there any do you have a very simple baseline that you could compare against? Or I'm very skeptical of attribution methods in general.
Yeah, that's a fair assumption, and unfortunately there aren't many papers published about attribution within LLMs. I'd say it's fairly new. Most of the research that we looked into came from last year. And so because of that, there's no unified benchmark per se. So what we had to do is just go through data sets that already had assigned ground truth texts within question answer data sets. And to speak to your skepticism about Lime in general, I think that a large portion of maybe why images don't work as well is there's significantly more data points in terms of pixels. And I think that because we're spanning them together and our weights are based on semantic distances, that it helps to defeat some of those hallucinations or wrong results. And we benchmarked as well, and we have, I'd say, strong results given the status of the field right now. Does that answer your question?
Thank you.
Yeah.
Great, thank you. Was there anything else you guys wanted to close out on?
One more from
Sure.
Paper answer.
Okay.
Yeah, just to clarify one thing, we are not running open source models in our production. We are running closed source models. But what we do is we use an open source model or proxy model to explain the generations. So we have also done some benchmarking to show, at least in our domain of data sets, actually open source or proxy models are good enough for explaining or good enough for attributing. So I think we skip to that part.
Yeah.
Great, everyone please give them a round of applause. This is Kunle. He's giving a talk on efficient AI inference. Please give it up for him.
Right. Thanks for giving me this opportunity to discuss with you guys, some very bright minds. Thanks to Eric for some previous discussions I've had with him, so thank you on that. This evening I'll be discussing efficient AI inference and how it goes way beyond what we see on the surface, way beyond low peak compute, or just arithmetic, if that makes sense. All right. Beautiful. All right. So my name is Kunle from Ishio Labs. We're trying to work on this, and then we've carved out some segment of the market that we can probably have some impact. Okay. Now, I love this picture because it represents, the most systems. What you see on the surface is just a fraction of what really goes on, the full picture. Okay, so I like using this kind of pictures because for AI inference pipeline, this picture is also representative. What you see on the surface is, normal training, everybody trains networks, and then we're good. And then we go back to relax, But for AI inference pipeline, we know that there's much more that goes on after training. Especially if you're servicing some markets, especially now you can tell that this is a very topical issue if you've been following the news, right? This is my turn. Okay. So you can tell that this is a very topical issue if you've been following the news, and then we hope to also make a difference in that area. So model growth is outpacing, hardware. I can see a lot of nodding right there. So you are not able to scale your hardware as much as these AI models are being architected, and that's a big issue. Inference also dominates the deployment cost. Now we're talking about if it's going to be data center scale. We're talking about, what is the energy you need, what is the cooling, what is all these resources you need to use. And at the data center scale too, now we also try to do this on the maybe embedded system space, but look at the big picture. At the data center scale, it's no more just efficiency. Efficiency is not just a metric anymore. It's becoming the currency for it to even operate. Because some communities are beginning to repel and say, no, we're not going to have you have this. So if you can have efficiency, it's good for everybody. It's good for the environment. And then energy limits and then latency is a very big issue. Yeah.
I guess that when all this started, most of the compute capacity was going to train new models. As now it seems that things are a bit going slower or stabilizing. What is the share that inference is taking in data centers? So it's an increasing share over time. How much compute is devoted to inference versus training?
Oh, okay. Are you asking about how much of inference?
Yeah, so how much computer capacity is devoted to inference, and if it's a share that is increasing over time, so little by little, the resources devoted to inference are way bigger than the resources devoted to training, or that's not the case?
There's a lot of factors. Your memory plays a lot of difference in that. Your computer also for sure, and then the lifespan of even your hardware, because if it's not properly cooled, your hardware lifespan just goes bad really quick, and now you have to replace the chip. So there's a lot of factors in that. I'm not an expert in the data center scale, but I can tell you that there's a lot of issues. Okay, but that's a big picture of what I'm trying to say. To show you that picture that there's a lot more that happens that engineers need to be aware of beyond just training. Okay, maybe some of your questions that I didn't get, maybe my next slides will answer them. So and I'll be here afterwards to take more. All right. So what really drives inference cost? So I used to be in the position where in the past I would be like, well, let's just train this model, and then we quantize. Somebody you're waiting for your math because your memory is too fast. Okay? Your memory is too fast and your math cannot keep up. Your ALUs and all that cannot keep up. Unfortunately, that's not the case in many of the deployments we see. These days, it's going to be more on the memory bound because your tensor cores are so engineered and tuned that they are so fast that the bottleneck is now moving the data from wherever you put it, if that makes sense. So moving data is not cheap, but compute is fast, okay? And that's the memory wall. By the way, my children saw that and they're like, you're going to use Mario Wall for that. And they asked me to tell you guys that they chose it for me. All right, so a quick scratch, back of the wall, back of the envelope computation there. Take this with a grain of salt, disclaimer. This is not a perfect computation. But take for instance, you have a 7 billion parameter model. Now, that's about 14 gigabytes, right? You can do a lot of optimizations on that model so that you can reuse, so that you don't have to always go fetch it. But let's just look at the time it takes for memory. To move that for a typical HBM, say 3 terabytes, and these days you put that from maybe 1 terabyte and upwards. You're looking about 5 milliseconds to do that. Now for the compute time, for the same, and this is, like I said, disclaimer, this is just representative. A sample hardware for FP16, the throughput for say 2000 T-flops per second, you're looking at about 7 microseconds. So your tensor cores are so fast that they're done. Now, most of the time you buy this hardware and you be like, well, I just got this new hardware, you know, you brag with your friends. I just got this new whatever model you got. But guess what? Most of the time it's just sitting idle. It's doing nothing. It's waiting for the memory. Okay? So in this case, even if we're wrong, say 200% of the time, it's still less than 0.1 milliseconds. Even in the worst case, 0.2 milliseconds. Okay? So we are wasting a lot of time on this. So tensor cores or your compute, your math, is not a bottleneck. It is always, in this case, most of the time, say on the LLM side or even on the CPU-based inferencing. Because we also seen some interest in, say, drones and some other smaller embedded systems that we don't want to use like edge GPUs because of the power we want to see. Even if we're going to sacrifice the time, you know, inference time, we want to sacrifice, we can still take the heat and maybe save more on energy. So we've seen a lot of interest in the CPU-based inferences also, not only on the LM side, but maybe smaller models, okay? So the cost of moving data. Now, this table is very old. This is from about 14 years ago from this classic paper. But, so you can tell that we're using a 45 nanometer. But these days we have better process nodes. But the truth is that the ratio is still similar, okay? The ratio is still similar. For your typical HBU or DRAM access, you're copying data, you spend about 2,600 picojoules, okay? And then for your normal tensor core additions, maybe from the last 3 rows down there, that would be the arithmetic, okay? So you can tell we're still under 4 picojoules for even FP32 multiply. How much more today when we have better hardware? But the ratio is the same. The whole idea for this slide is to show you that if you can save your post-inferencing, inference to let your math not, you reduce the memory traffic from the DRAM portion, you're saving a lot of energy, if that makes sense, okay? For instance, we have potential clients that maybe in the field, they have these power packs. Think about DOW and all people there. And then they have this kind of models that they just want to stay in the field more. If you can buy them more time, if their battery pack is not connected to the grid, they would definitely appreciate it, if that makes sense. All right, so now quantization. Everybody says, well, if you want something faster, you go for quantization. If you want something, maybe a bit more cheaper, you go for quantization. Now, in the past also, I used to think that quantization surface. From the picture I showed, there's more to it also. Say you quantize them from full precision to 8 beats and then to like 4 beats and all that. You would think that normally, well, because I have faster cores, that's the whole story. No. The story is that you are actually doing 8x less memory traffic. That's a big deal. Remember that? Okay. Remember this. So if you could quantize to like maybe integer 4 or NBFB4, whatever, 4 beats, that means with respect to the full precision you're saving, 8 hex reduction in traffic. So that means most of the time you're not operating a DRAM access row. That's a big savings right there. Remember I told you that when you do FP multiply, FP32 multiply, you're actually on maybe 4 picojoules. I would imagine that maybe int4 is also way lesser than that, say 0.01 picojoules or something. So the gains for your quantization is actually not really on the faster, regarding energy, it's actually not only on the faster tensor cores. It's actually because you're doing less on the DRAM access side. So if you, one of the reasons why you should be excited for quantization should not just be because I had faster tensor cores, it's because of the energy, okay? And also because, because of 8x reduction in your model size, you're able to fit more into probably, maybe you would not be storing your model in the DRAM. Maybe you can push it a little bit more to closer to the register. It's not going to be in the register, but maybe you can put it on this extra, depending on the hardware that you have. So it depends on the hardware you have. It could be NVIDIA hardware, you have to store the sheets. You have to look at the memory hierarchy and see where can I put this. So these are the kind of things that I want engineers to be thinking, if that makes sense. So when you have the quantized model, you just don't store it anywhere. Well, you have to understand this. All right, quantization models, I referenced 2 papers in the announcement. One of them is there. They have 180, actually 179 papers that they surveyed. And I actually put some out. I don't know if I spent time on this one, but does anyone know what QAT is? Quantization aware training and post-quantization aware. Anybody doesn't know? If you want me to go through that. Okay, so there are 2 major terrains for this quantization. I mean, these days it's kind of more hybrid because you can use them both. But for quantization aware training, you were training a network from scratch. Say 4 beats or 8 beats, you're doing that. For post-training quantization, you're doing afterwards. So generally, the QAT quantization aware training is often more, that's more expression. Okay, so it gives you more accuracy generally. And then I put some methods there. But the whole idea for the 179 quantization methods is that 1, you're going from full precision, that's 2 raised to the power 2, 4 billion parameters, 4.3 billion parameters, right? Sorry, 4.3 billion levels. And then you're going to say 4 bits, 2 raised to the power 4, 16 levels. Okay? So imagine that. And then what you're going to do is to be like, well, you're going to learn the range of your activations, the range of your channels and all of that. And you can decide which channel you want. Do you want to do group-wise? Do you want to do channel-wise? Do you want to do layer-wise? There's a lot. So all these models I see, they're a flavor of that. And because you're squishing 4 billion levels to like 16 levels, the range is going to be very off. The steps is going to be very off. You can decide to be like, I want to do uniform spacing. Well, floating points is not uniform. If you know your sine, manticore, and exponent, then you see that it's actually exponential. So you can decide to be like, I want to uniformize this, or I want to put it also in the log exponent or whatever. That's what they do. And then generally, I want to highlight the GPTQ. They're doing SCN. They're doing SCN. And then AWQ, they're trying to say like maybe some weights are better than the other. I think somebody, person who was here before also talked about regression. Maybe some weights are better than the other. So that AWQ has a flavor of that. And then the Q, the one that the last one there, there is a flavor of quantization methods that they try to rotate the outliers. Okay, so they will do some orthogonal transformations to rotate the outliers so that it's easier for them to quantize. For instance, if your range is too much and then you spread that on 16 levels, your errors are going to be different from when it's not that much. Okay, so all these methods are a flavor of that. And then common regimes for them, so W8, A8, that would be weights in 8 bits, and then activations in 8 bits. W4, A16 would be 4 bits weight, and then 16-bit activations. I remember, which other, it's a Chinese model that came up recently. They were doing W4, A16. For us, in our labs, we've done W4A4, and I can tell you some results afterwards. And then we've also done 1.58, 1000 bits. All right, challenges at this low bit weights is that the accuracy drops, like as you can imagine, right? And then the very big issue is what we call outliers. All right, so you can do all you want, all the tricks you want during training or during PTQ. You can do whatever you want because now you do it only on static weights. Okay, but when it's time for inference, now the whole game is different. Why? Because now activations are dynamic. They're based on the input, right? So you cannot actually capture the entire range of every possible input. So some models will be like, well, we've thrown some exceptions, put this one on the full precision path, or throw away something. But the issue is that when you have a very deep layer like that, few outliers can just collapse your entire quantization range. As you can imagine, because it's all propagating, right? When you multiply a bunch of layers, and then you see that it just keeps propagating. So there's a very big issue on the number 2 bullet point right there. And then calibration sensitivity, that's more on the post-trading, where you are calibrating your PTQ based on whatever data set you have. But that's not entirely representative of the entire possible data set that you could have. And then on the hardware support, I want to speak particularly on 4 bits because we worked on 4 bits. And then what we worked on is integer 4. And the reason why we chose integer 4 is because, I mean, we can still extend to other ones. But because there's a lot of backward compatibility with this integer 4, and because we can easily map integer 4 to the new files. So NVIDIA has this 4-bit system also. They call it MVFP4. Okay. So the reason is because integer 4 is just uniform, and they have good reasons for that. Okay. So you can tell that the hardware support is still not mature for 4 bits. Okay. I don't know if anybody has been doing 4-bit work yet. I would like to talk to you. But you can tell 8-bit quantization is very mature. 4 bits, especially with activations in 4 bits. I don't know if you guys understand what I'm saying. W4A32 is people are doing it. W4A16 people are doing it. But what I mean by that is W4A4.
Yes, I was hearing some months ago that there was a trend in the frontier labs to reduce the precision of the parameters of the weights in their models, and that it was not even to 16. No, now it seems that like the golden number is 8 bits. So I was wondering if is it worth to reduce the size of the precision so you can be more efficient in the hardware, and then just recover this lack of precision by making the model bigger?
Okay, yeah.
If I were OpenAI or if I were Anthropic, would you recommend this? Reduce precision and then just make the model bigger?
Yeah. I would recommend, but the problem is always the first bullet point right there. accuracy is kind of, accuracy drop is kind of synonymous to quantization. Whenever you hear quantization, you're like, what are we losing? It's math, right? What are we losing? We're losing something. However, at our labs, we've tried to cut, okay, I can say this. We've tried to capitalize on some other things that math also allows, which is regularization. So when you have this fine details that you are doing with, say, FB16, FB32, you're learning too much fine details, right? And you can tell the reason why we have all these dropouts and all that is for regularization in regular models. But 4-bit tends to have a very big intrinsic value, and all these lower bits, 8-bit, 4-bit, especially 4-bit, I've seen it a lot. They have a very big intrinsic value for regularization. So what we do is we try as much as possible without normally to be very close to the FP baseline, and then we now observe those intrinsic regularization. What we are seeing is like 0.5% on some models that we've tried, 0.5% lesser in accuracy to the baseline, and sometimes even higher than the baseline. It's just the way it is.
Yeah, go ahead.
Could you do things more about what models those were? You're getting such a little drop in accuracy. Were those like estimates, or is it?
Yeah. So we went for the kind of like Vision. We did CIFAR 100, which is like how many 100, you know, not just CIFAR 10, but we did CIFAR 100. And the reason is because we're targeting the lower, say, embedded system space. Okay, but the goal is to scale it up to elements also.
And so when you target these different hardwares, right? Like they obviously come with their own instruction set and stuff. So when you do that quantization, whether it's at 8-bit or 4-bit, I imagine internally in the calculation you dequantize, right, to like whatever it is, like half precision or whatever, to match whatever instruction set there are. Or do you still try to do the multiplication at that quantized level?
Yeah. So the integer 4 or 4-bit tensor core, they just want the 4 bits. Okay? Whatever you do outside that, you just want to be POT compliant. Like you want to do shifts only. So you don't want to say you multiply with an arbitrary number. You want to do some, POT. So as long as you do all this POT kind of thing, but you always fill in the right 4 bits into that, and just so everybody knows, these tensor cores, they don't understand what they're doing, right? Just throwing a bunch of 4-bit and then you get the output, okay? That's what we capitalize on. We try to represent what goes in there, and then the tensor core doesn't even know what it's doing. It's not regular math anymore. It's like abstract algebra and all that. And then whatever you get is just faithful to the hardware. But to your point, we ensure that whatever you do, dequantize, whatever, you always fit in the 4 bits, okay? And then activations also, by the time we get the normal accumulations out, we scale, we get back to 4 bits, okay? So the old goal is the table I showed you. You want to be in the region where you're not on the DRAM or HBM kind of level. And now because of integer 4, you can now reuse as many times as possible. You can fill in more times. We can talk more after this discussion. All right, I'll go into this. So I'm about to wrap up. 3 more slides. The key insight is inference efficiency is often the problem of memory traffic. Okay, memory traffic. As long as the physics is right, as long as we're doing everything unless something just comes tomorrow that blows the mind up, it's always memory traffic. And then low bit math works. Everybody is happy about that, but we need to reuse more of this traffic. So if you reuse more, that means you're not going back to the HBM to store it. You're always reusing right there. And one of the things you can do is, like we do, we write a lot of kernels to fuse as much structures together without going back to store them or something. So once you play around with all this, even beyond what the NVIDIA and Intel, Gaudi, or all these people give you, you can do more. And that's what we're targeting. All right, so the frontier that we see is a joint co-design or engineers that understand the design of algorithms and the systems together. Okay? And then at Ishiro AI, what we are building is an inference engine, and it's a memory traffic first inference engine. So you would ask and be like, well, maybe you're just another quantization effort. Yeah, but no. We do quantization, but what we're doing is very much on the memory traffic. We approach this along multiple axes. Number one is that we ensure that we re-represent the data that is going into the tensor cores, back to your question. So what that means is that we're doing something like a CPU, right? Your Z. Say you zip your files, right? So we're looking at the structure and we're massaging it. So we're massaging the structure losslessly. Okay? We're not, well, how do I say this without offending bad people? We're representing it in fewer bytes, but we're retaining the information. So that by the time we are done, it's actually exact same result. Right? Okay? So lossless, so we have two modes. The first mode is accuracy preserving structural optimization. That will be your regular FP16 model, or whatever model you have, and then you just make an inference and you're getting the exact same accuracy, bitwise. Okay? In fact, we got it to the point where we compared with FP32 and we discovered that we're off a little bit on ULP, and then we're like, what's going on? And then we discovered that actually within FP32 they're actually rounding half. You know, why we were not rounding off at one point. So we ended up benchmarking with integer, FP64, and we're bit exact. So I would say almost bit exact, and that's accuracy preserving, the exact accuracy you get. And also, so another thing we do is that now that we have reduced the structure and then we've massaged the structure, we get fewer bytes. We ensure that we don't rematerialize the zipped or the compressed version in memory. Because now if we do that, we just lost all the effort, if that makes sense, right? So the math is on the fewer bytes, the math is not on the uncompressed version. So it's always a one-way street for us. We do represent it and then we do inference on the fewer bytes. And that gives us the optimization and all the data layout and scheduling and all the things we can do on the kernel. All right, so back to the modes for the engine that we're building. It's accuracy preserving. Then the second one, the second mode would be aggressive efficiency gains, which would be the integer 4 that I just talked about, W4, A4. Like I said, occasionally we're even doing better than the baseline on some small models. Quick disclaimer, this is not to say that we're better than the baseline, but we are leveraging the intrinsic values of these regularizations. Okay? And then what we have demonstrated so far is just on the smaller models. So maybe when we get to the bigger models, maybe it's going to be something different. But so far it's been good for us. Then another thing we went to do is sub 2-bit. We tried binary normally, but we would kind of settle for now on 1.58. That's going to be ternary. So you have -1, 0, and 1. Remember the table I showed you? Wow, that saved a lot of energy. Why? Because now, come on, what's the weight of the size of your weights? Very, very tiny, right? In fact, you can pack it to 1.5, right? Log 3 base 2, right? So with that, we have -1, 0, 1. But apart from what I'm showing here, there's a lot that goes on in what we do. So when I say W4, quickly this disclaimer, this is not exactly 8 hex. It's going to be, say, 7 point, maybe 6 something for us because we add a little bit overhead to what we pass along to go to the map. Okay, so very, very close. probably we can add more language too. We are so we've partnered with a household name CPU OEM here in the US, and then we're doing some piloting very soon, hoping to test on their suite of CPUs and maybe the GPUs too, hoping that, fingers crossed, everything goes well. So that's what we are doing, and we're local here in Austin. Closing thought before I take more questions. Okay.
So are you doing FP or integer or just symbolic, just if statements?
You're saying that are we doing
Yeah,
FP?
when you, the actual assembly, where are you using, like the actual command that you're getting executed on the core, are they FP or are they integer?
Integers.
You're integer?
Yeah. There's not a lot of documentation right now. I can talk to people like Eric Moore, but we've finally able to see, we've written the kernel for integer 4. The GPU I have and the few hardwares I have, there's integer 4 tensor core on that. We would like to expand to more tensor cores, but we need documentation and work with teams. Yeah, so, yeah.
Great. Do you want to just finish your closing thoughts, and then we can do more questions later
Yeah.
if you're not working?
Yeah. All right. So this is the closing thought. Compute is cheap, like you can tell, right? I was blown away that FP32 can be so tuned that actually maybe you're not even. It can be almost as fast as some integers actually if they tune it so well. I was shocked. So compute is cheap, but data movement is not. It's expensive. So as long as physics is right, as long as Einstein and all these things are with transistors and everything on the SRAM, DRAM, all these technologies, as long as they're right, inference efficiency will be won by those who move fewer bytes, and that's what we're trying to do. I'd like to talk more after this bit, but I can take questions now.
Thank you. So, you have 20 minutes to hang out here, after which you can just keep talking outside of these glass walls. And again, if you came in a little later, if you park downstairs in the garage, come see me afterwards to get valid parking validation. Please join our group, please give us 5 stars. And if you're working on anything interesting, whether you wrote a paper or whether you found a paper that you really like, that speaks to you, please let me know. We'd love to have you as a speaker. Or also if you're working on like something that's applied AI, maybe it's like a startup, maybe it's a new product or a new project at a larger company, or it's a personal project, even open cloud really would be cool. We haven't had that yet, so just let me know. But thank you, and yeah, please sign up and you can hang out here for 20 minutes.